In the big picture, what we're talking about is how contaminants move in the subsurface. And so we can divide it up into maybe a few different time regions. First is when you dump it in the subsurface in the first place. If it's a non-aqueous fluid, then it will sink into the soil. If it's denser than water, it will go below the water table. If it's less dense than water, it will be cupped by the water table. And if it does go through the water table, this is a NAPL, then the behavior you'd get would be a chimney, which is a smeared zone. And this would act as a source area for dissolution that gets carried downstream. You see the plume on this is on the right-hand side of this, clean water on the left-hand side, upstream and downstream sides. And it would carry it downstream to some kind of compliance point where you would want to be able to see how large that concentration was. And so understanding the architecture of this, whether it exists as a smeared zone or whether it exists as little discrete pools, whether it's gone all the way down to the base of a capillary barrier, or whether it has kind of feathered itself into lots of little discrete zones, is something we'd like to know, because that's the source that defines what the plume will look like. And if we want to remediate the plume, then that would be some information that we'd like to be able to have. And so last time we started talking about the first 3 months. Drop it into the ground, it finds this architecture within the first couple of weeks, few months, whatever, and then this is in place for the next 3 decades to be the problem that you want to be able to solve. And so the question is, how do we decide whether it will look like this, or whether it look like this, or like this, or like this? What are the controlling behaviors? And so that's what we would like to address today, or continue addressing, I guess. And so in terms of a recap, you might recall a couple of things. The first is that we talked about behaviors in, whoops, I didn't want to write with a blunt object. So you remember the last time we looked at behaviors of capillary tubes. And by analogy, we also looked at the behavior of fractures in terms of the rise height of fluids within each of these as some critical height below a level of fluid. And we identified a couple expressions. One was that the height rise, critical height, was something like 4 times interfacial tension divided by the unit weight of the fluid and the diameter of this tube. And in the case of a fracture, the height rise was something like 2 times the interfacial tension, unit weight of the fluid, and the aperture, the separation between these 2 parallel plates. And we did that not so much because we're interested in how much it rises when you put a capillary in the fluid. We're much more interested in the idea that if we, I'll come back to this. If we had a fluid sitting in a porous medium, we'd much rather be able to figure out exactly, for instance, what height, if you imagine this as a tube sitting here, what height of fluid giving you a pressure at this particular location allows this to go down here. That's basically the geometry that we're interested in. And so what we'd like to know is, what is the saturation going to look like in this whole bead pack? Coarse bead pack, fine bead pack, large pores, small pores, and what are the physical properties that define that behavior? And so this is the analog that we use to define that. So we could think about it, I suppose, in terms of the height rise that occurs in fluids going up there. I suppose we could also think about it in terms of the fluid pressure that we'd have to apply at this point here be able to drive this fluid along there relative to this interfacial location. And so what we could do is we could multiply this by both sides by unit weight of fluid. So if you take the height rise and you multiply by unit weight of fluid, that is what we call a capillary pressure. Capillary pressure is a difference in pressure between the non-wetting fluid and the wetting fluid, by definition. And so if we multiply each of these expressions by unit weight, we end up with capillary pressures being equal to 4 times interfacial tension divided by diameter, or in the other case, 2 times interfacial tension divided by the aperture B, just by multiplying each of these expressions both sides by unit weight. And so that's useful to us because it tells us what kind of pressure we have to apply to be able to push fluid through the system. And if you remember, the last thing we finished with was this little thought question. What happens if you're trying to push a bead, a bubble of this red fluid along here? It'll go through this wide area really easily, but it'll get hung up on the small area. And so the architecture of these pores and their constrictions and their openings is important, because there would be a very different behavior in this right-hand one to the left-hand one. All the beads would just happily be able to go through this large opening, but they'd get hung up here. In this case, I guess they'd get hung up at this first bead, and unless there was a really big pressure behind it, it wouldn't move any. And so that's the behavior that we like to be able to explore. And so what we can do is we could think of this, a porous medium, as a bundle of capillary tubes, which together represent the porous medium. And then if we know that, then we know what the pressure is that we have to apply to get through each one of these tubes to make it advance into the subsurface. So that's kind of our big picture. But that's not completely useful to us, because if we come back to look at this behavior here, we know that if we take, we're not really interested in the behavior at this single pore throat that the pen is on right here, but we might be interested to know what the amount of fluid is within this box if we look at it here. And so we could look at how much of the red fluid exists in here and how much pore space that includes. And we could look at the zone in which it's not filled. It's only filled with either water, if this is below the water table, or it would be air if it's above the water table. We could look at the relative saturations of those. And that's a much more interesting question for us to know, because one, we'll find out that this saturation says something about the permeability of this material, in other words, to water going across it, which we'd like to know. And it also says how much stuff is in place in the subsurface and how much we'd have to remove if we want to make it pristine again. And so that's the kind of question that we would like to answer. And so that means that maybe instead of answering the case of what pressure do we have to apply to get fluid to move along this capillary, another question might be, what pressure do we have to apply if we have a bunch of capillaries that exist, some of which are big, some of which are small, some of which are intermediate size, etc., which represent the real porous medium. So we could use these formulae, I suppose, to be able to calculate that. Or we could take another step and we could just take some real material and try messing around with that to say something about what behavior we'd expect to get if we use that. And so the geometry that we'll take, I'll come back and draw it on a page. The geometry we take, I'm skipping ahead, but I think that's okay, hopefully I can find it, is this geometry here. And so let's take a core. Take a piece of the aquifer by drilling, take it back to the lab, and then this is the piece of core that we take back into the lab. The core has water in it initially, And what we're going to do is we're going to put another fluid around it. It could be air, but let's assume it's a NAPL, NAPL, non-aqueous phase liquid. And so what we could do is you could imagine that we would increase this. So we take this core, we put it in here, we put it on top of a frit, which allows some fluid to go through it. So a frit is just a fancy way of saying some sieve that allows fluid to go through it of some specific interfacial tension. So it has a bunch of little holes in it to allow some fluid to go out. And then in this we put a seal with a rubber stopper in place. And inside this seal we put an NAPL and we put a pressure. And so what we could think about is with this pressure, it could either be just a straight column of water which had a certain height to it, and if it had a certain height then it would apply a particular pressure in this fluid here because it goes through the stopper into this chamber, or we could have a nitrogen pressure behind it that was driving it. Doesn't matter. And so what we'd like to do with this is to do an experiment. And the experiment would allow us to draw a particular graph bit shaky hands there, which we'll call a capillary pressure saturation curve. Versus saturation curve, I guess. And so maybe not surprisingly, since we're calling that, the units of this are saturation from 0 to 100%, and it's water saturation. And you'll remember that the definition of saturation is what? It's the volume of water divided by the volumes of the voids, or the pores. So if there's no water in it, it's 0. If it's 100% saturated, then all of the pore space is filled with water. And on the vertical axis, we'll draw capillary pressure. And just to remind you, capillary pressure is the difference between the pressure in the non-wetting fluid relative to the wetting fluid, water. So the wetting fluid is probably water. Can you see that? It's probably quite large, isn't it? A bit blunt. I realize it's a bit blunt on the screen. And the non-wetting fluid would be the NAPL in this case. Or in this book, it's oil. And so we start off with no pressure here. And so if there's no pressure here, the capillary pressure is, the water pressure is 0 because it's just sitting there. It's as much fluid that's in the core. It's just sitting in there, has no real height to it, so therefore the pressure is very, very small. We add a pressure of the oil around that. As the height of that pressure gets, the column of that oil gets larger and larger, the pressure of the non-wetting fluid will be larger and larger, and this won't change, and so the capillary pressure will grow. And so what we could do is we will make some, let me do this. So what we'll do is our first point is here. 0 pressure in the water, but essentially 0 pressure in the oil around it. It's only got a small head on top of it, and so these are both 0 and there's nothing there. We increase the pressure in the oil, and so this increases, but this stays 0. This is always going to be 0 in our case. And so we're here. If the pressure difference between these is not large enough for us to physically push a bubble of this oil into the pore sample in the largest pore throat, then the saturation of water will still be 100%. If we increase it again, and it's still not big enough to get into the largest pore, it will still be 100% water saturated because nothing has come out, and this stuff is still trying to get into it. In the next step, all of a sudden, when we put it up to the next pressure here, it allows a small slither of this other fluid to go into it, then by definition the blue phase has some small saturation and the water phase has somewhat less than 100% now, which is this amount here. So this would be our new equilibrium point. We increase the pressure, slowly some fluid would go into it. We don't care about this pathway, but we do care about this end point. We let it reach equilibrium, we put up the pressure again. Put up the pressure, it invades some more, and slowly, as it does this, by the way, it pushes the water out through this bottom one into here. And of course, by conservation of volume, this height would go up. So you could measure the saturation just by the amount of fluid that's displaced, or you could measure it by the amount of fluid that invades. The blue fluid is invading, the gray fluid or the red fluid is being displaced. They have to be equal to each other. And so we have another point here. We do the same. We do the same with a variety of increments. And so as a result of that, if we wanted to draw this capillary pressure versus saturation curve, I guess if we did it in much smaller increments, we'd be able to do it, but we get a relationship which is this, whoops, this curve here. And you'll get to draw with these in one of your assignments, by the way. And so in other words, it goes here. Now if we did the opposite, if we decided to stop here and we drop the pressure, so I could, I guess, draw little arrows on here if I wanted to. So now we're going to drop the pressure, and it goes to this new point. We drop the pressure, it goes to a new point. We drop the pressure, it goes to a new point. We drop the pressure, it goes to a new point. And so if I just join these up, I won't join it up here, but I'll go from this point downwards through these joined points. And it's a horrible diagram. I realize it's not exactly smooth, but you see two things. One is that as you start increasing the pressure of the oil, then this blue fluid invades it and it goes along this trajectory here up to some point. Right up here it will start going vertical, and then when you come back down again it will come in this direction. And so what this is, the only thing to look here, we don't care about the blue curve, which is this stair step. That's just our means to be able to get the green curve. But this capillary pressure versus saturation curve here tells us exactly what the overall saturation is at a particular pressure. And so if we wanted to, at any given pressure, we could just draw a line across here, and it would tell us something that's a bit ambiguous. It would tell us what the saturation is of the fluid, but unfortunately it gives us two values of that saturation, these 2 points here. And so it matters as to whether we're forcing oil in and water out, or if we're allowing water to imbibe back into the sample. It matters what trajectory we're on, whether we're going up or down. So it's ambiguous. Or if we had a given saturation, probably this might confuse things too much. At any given saturation that we choose, also we end up with two magnitudes of potential capillary pressures. It doesn't matter that they're the same. And so rather than use those expressions that we've talked about for bundles of capillaries or for fractures, which are important in our kind of understanding of why this occurs, it's interfacial tension that's acting against the weight of the fluid, which is controlling its saturation. The weight of the fluid and the column above it says what the pressure is, and therefore defines this capillary pressure here. All of the things that we'd like to know about this system are really controlled in this given experiment. So we can think about the value of the capillaries and the fractures in defining what the physics are of what's going on, but if we ever want to know what the saturations are in a system like this, then we can use these capillary pressure versus saturation curves merely by taking a sample of the soil or the rock and doing this kind of experiment to it. And so these are one of the two key relationships, I guess, that we'll work with in looking at multiphase flow. Capillary pressure versus saturation curve is one of them, and relative permeability versus saturation curve is the other one, which we won't talk about today. All right? So, if you understand that, you're more than halfway there in terms of going where we're going. I didn't want to do that, did I? All right. Everyone copacetic with that? So we jumped ahead a little bit, but all you need is that figure. So the big picture point is that why is it doing that? Yeah. That's why it's doing that. So the big picture point is that we can define these component conduits, capillary and a fracture. They say something about entry pressures, but they're not completely useful to us because we want to know what the ensemble behavior is. And if we want that ensemble behavior is to be, then what we can use is this capillary pressure versus saturation curve. And this capillary pressure versus saturation curve will always look like this. I can probably draw it better here without all the abstractions. And we'll look at some more in due course. This is capillary pressure, which is the non-wetting pressure minus the wetting pressure. Pressure of the wetting fluid or the pressure in the non-wetting fluid. Pressure in the water, pressure in the oil. And the saturation of water, going from 0% to 100%. And that's it. And so if we can arrange an experiment to be able to get this curve, then this curve supplants this. Interestingly enough, I haven't drawn this very well, but where this curve comes away from this, so in other words, say this is where it deviates from 100%, this is what we'll call PC0. And PC0 is basically this. 4 times interfacial tension divided by the diameter of the capillaries. And so we've said already that we're going to have capillaries of many different diameters. Which capillary do you think this would be? Largest or smallest? Who's going to be brave and engaged? Or shall, yeah, just shout.
Small.
Why small? Yeah, but this is a higher pressure, right? Even here. So it'd be the smallest, right? This is the lowest value where it goes in. The right rationale. But this is, so as you increase the pressure, the one it will go into first is the one where it will take the lowest pressure to go in. And as you keep on increasing this pressure, it'll progressively go into smaller and smaller ones. So, good for you. Good. Well done. So this represents the largest fracture. So this also, I guess, to back up, is why fractures are so important. Because fractures are typically much more open than the individual small pores in the rock that makes the wall, in the pores that make the wall rock of these fractures. And so these will typically act as the conduits, the entry conduits. All right. So, what we can do, and so we've talked a little bit about these curves, and these are perhaps a bit slightly nicer pictures of these curves. We've noted that they're capillary pressure versus saturation curves. We know that the scale on the bottom goes from 0 to 100%, or 0 to 1 if you do it as a fraction. One thing you can also do is you can scale it in some way. We won't talk about the scaling today, but just notice that it is true. And that is that in the same way that we can define where this bubbling pressure, PC0, occurs, this is what we just called PC0 on the upper case. This is PC0. Capillary pressure for 0 saturation of the non-wetting fluid. So I guess the other thing that we could draw on this figure is that this is the water saturation going from 0 to 100%. The saturation of the non-wetting fluid would go from 0 to 100%. Because we know that the saturation of the non-wetting fluid plus the saturation of the wetting fluid, by definition, have to equal 1. They have to fill the pore space. If there's a third fluid, then the three of them would have to sum to 1. In this case, we're only talking about 2 fluids. But anyway, we digress. So the main point here is that we can draw these capillary pressure versus saturation curves, saturation, capillary pressure, but instead of putting on the vertical axis the capillary pressure, what we could do is we could use a scaling parameter. And this scaling parameter, these are sometimes called J curves, or Leverett J curves. Because instead of plotting our data relative to capillary pressure, what we could do is we could do the experiment we just did. We could take the magnitudes of the capillary pressures that we measured for all of these little data points that would go on this curve, and we could divide it by some parameters. And the parameters would be interfacial tension, the permeability of the rock which it's being pushed into, and the porosity of the rock. So they're all defined here. You could check that this is a non-dimensional parameter. We take fluid mechanics for a reason. Capillary pressure is in pascals, which is newtons per meter squared. Interfacial tension is in newtons per meter. And permeability is in meters squared. Porosity has no units. And so meters squared square root is meters. Meters times meters, meters squared cancel out, and newtons cancel out. And so it has no units. And so what's interesting, and what I would dare say is cool about that, is that the intercept for this is always at a magnitude of about 0.3. It doesn't matter if it's sand, gravel, granite, shale. Once you do this scaling, this universal scaling here comes to a value of something like 0.3, and we'll talk about that in a couple of weeks, why that might be the case. And that is always one particular ordinate. So you could always say that capillary pressure at entry is equal to PC0 divided by interfacial tension and multiplied by permeability over porosity square root is about 0.3. And so the interesting thing for that is that this entry pressure is something we'd like to know, because it says something about when the fluid will invade. We often can't get this very accurately, but if we know that this value is always about 0.3, if we can always measure the interfacial tension of the fluids, which we probably can from a textbook, if we know what the permeability of the rock is, which we can often get, and we know its porosity, then all of a sudden we only have one number here that we need to get. And so we may be able to use this entry pressure in some useful way to be able to say whether stuff has gone into the subsurface or not, and if it has gone into the subsurface, how deep has it gone, and is it like a string of a chimney, which is at very low saturation, or are all of these little lenses present, as we talked about in that previous figure. So, if we look at dividing up this figure, we can put some bounds on it. This is the entry pressure. So PC0 is the entry pressure. The pressure that you apply to get the first non-zero saturation of the non-wetting fluid. This is the irreducible saturation of water. Fluid. If I draw down this thing here, this is the irreducible saturation of the non-wetting fluid. And if you look at this figure, you'll realize the axes. The water saturation on the bottom goes from 0 to 1. The non-wetting saturation at the top goes from 0 to 1 in the opposite direction from what we've said. And these kind of limiting behaviors, the irreducible saturation of water at one location and the irreducible saturation of the non-wetting fluid, where this value here is 0.87 saturation of water, are two kind of bounding values. And so in a physical sense, what this means is that if you start off at this point here, you're 100% water saturated. You try and push some oil into it, and as you increase the pressure up to this point, all of a sudden you get the first slither of oil going into it. You keep on increasing the pressure, you go up and you get more and more oil into it until you can't get any more into it. At this stage you have, say, 80%, 90% oil in it. And you have 10% water remaining. This is the 10% here. And so you've pushed as much oil into it. It's got some water held in the spaces as it had before, and that's as much oil as you get into it. You push as you like, increase this pressure all the way up to infinity, you won't get any more into it. Now if you reduce the pressure of the oil that's on the outside, what it'll do is it'll imbibe, it'll suck water into it spontaneously, and it will come down this trajectory here, but it will reach this irreducible saturation. So at this irreducible saturation, this is the maximum amount of water you can get into it, which is 80% water, and there's 13% of oil that you can't get out by any means that you want, 0.13. And so that's what these two irreducible behaviors represent. Maybe for those who think of this more visually, it's perhaps worthwhile going back to this figure that we looked at yesterday, Thursday, which is a key figure. And so what we're talking about is a water wet sand. We start off, this is kind of how we start off. If you imagine these little blobs of oil not being there, this is how we start. Fully water saturated if it was all clear or white within the pore space. As we push in oil to the system, little bubbles of it come in first, more of it invades until it ends up at a large saturation of oil. The only water that we have are these little, what we called pendular rings. Grain on grain, there's a donut that goes around it, and there's a monolayer of water in contact with the grains that you can't really see here. It'd be white in contact with here. And this is the case. Where are these places? Where I'm going to draw it. If you think about where on this little diagram we might be, this is capillary pressure, this is saturation of water, this is saturation of the non-wetting. We start off here. Imagine that we don't have any blobs here. This is where we are. If we increase the amount of oil, we push in a bubble, and all of a sudden we found ourselves at point number 1. We keep on pushing oil in, we move up here, and we keep on going up here, more and more oil, so we're almost at the irreducible saturation here. So physically, this diagram is just allowing us to quantify this behavior that we talked about in kind of descriptive terms before. And what it does is it allows us to say exactly how much the saturation of, how much mass of this contaminant is present that we might want to get out of the system. And so start thinking about things in terms of these curves. Okay. All right. So that says something about what's going on. I'm not sure. What do we have to worry about here? If you look, actually these just relate to some figures that are here. Looking for those figures right now. Tell me to. Yeah, these figures. So you could imagine that maybe if you did a bunch of experiments that we've just talked about with a whole bunch of different sands, so these happen to be petroleum reservoirs, and we did the experiment where we kept on increasing the oil pressure, we'd end up with a bunch of trajectories where they're slightly different. They are different, but now they're not so different. So you'll see that if we do this for real sands or reservoirs or aquifers with this same scaling relationship, we don't quite get the 0.3, which is the theoretical value, but we get things that are pretty close to that. We get them within 0.45 to 0.1. And in the systems that you're going to work with in the subsurface, that kind of range of variability is really quite small. It's a factor of 2 or 3, but compared to things like permeabilities that can vary over 5 decades, 5 orders of magnitude, that kind of variability of a few times is really not very much. This is the curve we just talked about that I drew out, and it starts at 0.3 here and goes up. And this is the 0.87 that we talked about. And these are the two different curves that we have. They're referred to as a drainage curve because I don't know if it's termed that because it grew up in the oil industry or the agricultural industry. It's draining water. You start off 100% water filled and you drain water out of the system as you increase the other phase. In petroleum reservoirs, that other phase is oil that's in there. In the vadose zone, that other fluid is air that's present above the water table. But regardless, it's drainage of water as you increase the capillary pressure. As you decrease the capillary pressure, you come back here and you imbibe water spontaneously back into it. So the drainage and imbibition is referring to the response to water. Okay, if we were to do a thought experiment and plot, great heating system they got here. If we were to do a thought experiment and run those kinds of experiments on different samples, what could we say about the pore size distributions in terms of the magnitudes of the pores and their distribution between whether they're narrowly confined, only big pores with a very narrow standard deviation of pore sizes, or big pores with a very broad standard deviation. Can you say anything about that from these particular plots here? If you took sand 1 versus sand 4, does sand 1 have the largest pore space? Is it larger or smaller than sand 4? Got it. So low entry pressure must be larger because we know that capillary pressure is proportional to diameter, no, inverse, right? Interfacial tension divided by diameter. So we know that this particular pore space must be larger than this one because it takes a larger pressure to go into it. They also have very different shapes. 1 and 2 have, so actually 2 and 3 have basically the same entry pressure, right? So you'd expect for this one that maybe the largest pore space might be the same for each of them because they have the same entry pressure. What about the grain pore size gradation? Which one is broader distribution? 3. Yeah, right. So in other words, these are basically, once you invade here, you invade all of the volume of the pore space, because this is almost horizontal, as opposed to this. So there's something we can say physically about the shapes of the distributions of the pore size, and that's the linkage between the measurements that we do on core, which is what this is done by, and our kind of understanding that we have from the pore throat sizes, which is embodied in this expression here. So it's a useful thing to be able to do. So, okay. All right. I skipped to that, but that's fine. So what we could do, and we'll use it, we don't need to know so much about it right now, is that we could also do something with these figures of capillary pressure versus saturation. So one thing that we have done is we said we could take the measured capillary pressures and we could divide it through by interfacial tension and multiply by the square root of permeability and porosity. And that would allow all the graphs to fit on top of each other. The other thing that we could do is we could manipulate this in another way to make this graph, which is kind of complicated and has some curves in it, a much more simple graph. And so one way to do that would be to define the saturation not in terms of the actual saturation. So this is the actual saturation of water that we'd measure in an experiment. But we could measure it relative to the irreducible saturation of water. And so you'll recall that on this particular plot, this term here, this term here is the irreducible saturation of water. It's about 10%. So this is the maximum amount of water that we can get out of the sample as we push another fluid into it. So it says that we always have about 10% water left in the sample as we try and evacuate it. So if instead of plotting the saturation that we've done here for each of these capillary pressures, we plot an effective saturation, which is merely the saturation minus the irreducible saturation, divided by 1 minus the saturation. And so if you think about what this equation is that the saturation minus the irreducible saturation means that we're just lopping off this portion of the graph. So in other words, we're just imagining that this part of the graph doesn't exist, and that instead of the graph starting at 0 and going to 1, it actually starts at 0 here and goes to 1. So it just changes the scaling. If you think about this, this is exactly what it is. We subtract SW0 off here, which is this length, and we subtract SW0 from 1, which is this length here. So it just makes it the scaling. So it changes the scale being from this extremity to here to this intermediate boundary. So we do that. We do one thing, we change the scaling, and then we plot them as log scales. So if we take exactly the same data that we have here on this figure, and we plot it in terms of effective saturation, and instead of plotting it in this form, we plot it as a log pressure versus a log saturation, then we get curves that look like this. We take a curve that was this, which is the ones we've just looked at least in the drainage curve, right? This is drainage. And if instead of writing this just as a natural scale, we write it as a log scale, which is this, we switch the axes. And if instead of writing this as a capillary pressure, we divide it through by the unit weight of the fluid and take it as a log and replot those data, then this graph exactly plots like this. It might seem like a futile idea. Why would we do that? Stupid, right? Well, we do it because we find out that if we do it, instead of having a complicated curve, we actually get a straight line with an intercept. And so remember that these two figures are exactly the same, they're just plotted differently. It's divided through by unit weight, and they're plotted as log instead of natural figures. And if we do that, then we end up with, this is our bubbling pressure, PB0, or kind of, because it's normalized with unit weight. And instead of having this curve to it, it has a particular slope to it. But if you think about it, we could do exactly the same thought experiment that we did before for these other curves. If I just switch down here. Remember, we did a thought experiment to say which one has the largest pores? This one, of course. Which one has the smallest pores? This one does. Which one is most uniformly graded of 2 and 3? This one is most uniform. This one is least uniform. The rationale is that once you invade this one pore space, all the other pores are the same size, so it just fills the whole sample. We could do the same thought experiment with this new plot that we have, because the data on this figure are plotted as log capillary pressure over unit weight, and you can't see this very well, but this is log effective saturation. So if you plot 1, 2, 3, and 4 on this curve, you get exactly the same differentiation, if you like, between those curves, and they kind of say the same things. The entry pressure. The lowest capillary pressure has the largest capillary opening. So number 1 should be this one here. This has the lowest entry pressure, and so has the largest pore space. And the slope of these individual curves say something about the distribution of the pore space. If it were exactly a vertical curve, that would say that every single pore space was exactly the same throughout the sample. So this would be a uniformly graded sample. All the pore space is the same. And one that went across here would be a broadly graded sample. Likewise, one that had the pore size here, this would be large pore. This would be small pore. This would be uniform pore. This would be a broad distribution. So we can make those linkages between, not surprisingly, between these figures when we draw them in natural space or log-log space. And the only reason to draw them in log-log space is that we can make a very simple equation that represents an intercept and a straight line, y equals mx plus c, right? But in log-log space. And so by recognizing the fact that if we replot these, they become an intercept and a straight line, then we should be able to write an equation that describes them. And that equation is this, which merely says that you can represent these kind of complicated curves with a very simple equation which relates the log of the effective saturation, which we defined here, with a log of a capillary pressure divided by the bubbling pressure. So if we wrote that out in terms of what we've talked about, this would be the log of the effective saturation is equal to a slope. This is a slope, y equals mx plus c, I don't know what you use in the US, multiplied by the log of the capillary pressure divided by what we've called PC0. This is our bubbling pressure. And so-called bubbling pressure because this is the pressure you have to apply to push a bubble of this invading fluid into the largest pore throat that you can find. And so physically what it represents is this point here, which is the same as this point here, which is the same as this point here, which is the same as this point here. So that's the commonality between them. So we calculate the invasion pressures for capillaries, not much use to us because we know that porous media are all different sizes of capillaries. We could do an experiment on a real sample to be able to see what these capillary pressure versus saturation curves look like. and that would say how saturation varies as a function of the pressure that we apply. And we can plot it in log-log space because that makes the equation really, really very simple as this. And so that's kind of where we've gone on this little journey today. And so we've said something about being able to classify exactly what these saturation curves look like. And our reason for doing that, of course, is because we want to be able to go into the field, and if we know something about the porous medium, we'd like to know what the saturation is. Whether it's just a smear of this oil in here, whether it's a puddle of this oil that sits in the subsurface, and what is it that controls where those puddles exist in terms of the architecture of the pore space within the subsurface. So that's kind of where we like to be. So right now, what we have is we have something that allows us to say a little bit, at least, about this saturation, because we have curves that say something about capillary pressure versus saturation. Oops. And we know that these curves look something like this. So now the next step is, how do we use that to be able to figure out what is the saturation of this? How do we know what the saturation would be at this particular point, at this particular depth below the water table, to be able to figure out exactly where in this curve we think we'd find ourselves? Incidentally, where would we be, right? What would we think we'd be here? So we have a little representative elemental volume. It has a lot of white space in it, which would be water in this particular case, and a bit of red stuff in it, which means that some of the pore space is filled with the NAPL, but probably not 100% filled. And so we would be at some saturation which is not really 100% water saturated, but maybe, I don't know, maybe 80% water saturated. So we'd be somewhere here. So how do we use this curve that we have here, which is our information, to be able to figure out exactly what that would be? And so that's the next task that we have. I think next task we have. Yeah, we have plenty of time for that task. Let's do it straight, and we'll come back to this other figure. So this is what we could do. And this sometimes is a bit mind-altering, I think, but I think we can get beyond that. So this is what how we'd like to think of it. The easiest way to think of it probably is on the right-hand diagram. So let me blow this up. So these figures represent something which is, in a physical sense, this is the surface of the ground, an unsaturated zone, the tension saturated zone, which is the capillary fringe, and the water table. So this is the vadose zone that fits above the water table, or sits above the water table, with the saturated zone below that. On the right-hand side of this figure, we have a water table that exists at the surface, and is the groundwater zone everywhere below that. So we're trying to represent two different conditions on one figure. And so what we'll do is we'll look at each of those, the right side and the left side, separately. The easiest one to talk about is the right side. And so I am going to see if we can do this. A bit too big. So what do we need to know? You'll recall that we had a figure that looked like this. You'll get sick of these labels, but it's actually useful to maybe repeat them, because we know that it defines saturation from 0 to 100%. We know that it represents capillary pressure. And we know that the curves look like this. Let's just do the one curve for now. This is the drying curve, as we've called it. Drying because water is drying out from 100% to 0%, 10% as we dry it. We recall that the definition of capillary pressure is the non-wetting pressure minus the water pressure. What we could do is we could realize that this capillary pressure here is 0, and this capillary pressure here is large, non-zero, positive and non-zero. What we could do is we could flip this figure over. If you take a mirror image of it, then it would look like this. This is 0, this is large. This is still capillary pressure, and this is still saturation of water. Right? Done nothing else other than that. So you notice now that this figure here looks exactly the same as the figure that's underneath it on this figure. Okay. So this is our capillary pressure versus saturation curve. So what we could do is, if we knew what the capillary pressure was within the subsurface, we could exactly say from that capillary pressure, this is the saturation that we expect at that particular depth. So if we can convert capillary pressure to a depth, Z, then we can say something about what we'd expect the saturation to look like. And so that's what we're going to attempt to do. So the rationale for this is to look at what those capillary pressures would be. So we have a water-saturated aquifer, which is saturated in this blue fluid, water. And we try and push this oil into it, which is this green little slither, which we've tried to push into it. If we were in a swimming pool full of water, we know that as you go down in the water, the pressure increases as 1 over the unit weight. Your ears feel it. And so this equation for this curve is just that the pressure, not capillary pressure, is equal to elevation times unit weight of water. There's a negative sign in there depending on your sign convention, but we're not using that same sign convention. In fluids we use a sign convention, Z is positive up, but this is positive downwards. So this would be the pressure you'd feel in the swimming pool, just in the water. We don't care that there's actually solid grains around this, that we wouldn't actually be able to get into this, but if we were very small, I suppose, we'd get into the pore space and we'd feel that pressure. This is a NAPL. It's denser than water, and so if we looked at the pressure in a swimming pool full of NAPL, that would be the green curve. It's again the same as this. The pressure is going to be equal to the depth multiplied by the unit weight of the non-wetting fluid. Since the unit weight is larger than water, it has to be a shallower incline. Our definition of capillary pressure is the difference between the non-wetting fluid pressure and the wetting fluid pressure. And so if you look at sitting here, right on the boundary between these two fluids, in the green or in the blue, this is the fluid pressure in the green, this is the fluid pressure in the blue, water, and the difference between them by definition is the capillary pressure. So this physically is the capillary pressure. And if we wanted to just define the capillary pressure in terms of these, this is the non-wetting fluid pressure, this is the wetting fluid pressure. Capillary pressure is equal to the pressure in the non-wetting minus the pressure in the wetting, which is this value here. And in a physical sense, it's just the difference between those two curves. It starts off at 0 at the surface. It gets to be some bigger number as you go down. And you could calculate exactly what that capillary pressure would be from this equation. If you go twice as deep, then the capillary pressure difference will be twice as large. So it scales directly with this vertical axis. So you get the picture. And so what this picture tells you is that if you try and push this fluid in there, you actually can't get it in there unless you provide some kind of surcharge, say with a barrel that puts it in there and actually physically moves this line over, because it's got to get to this point before it breaks in at some non-zero saturation. But once you get below this point, then it can actually fill this up. And so at this particular point here, if this capillary pressure is equivalent to this depth, so this is really a depth here on this chart, but it's an equivalent capillary pressure here, then the saturation at that point would be equal to this. And what would it be? It would be equal to, I'm just scaling this off, it would be 60% water, and it would be 40% NAPL. DNAPL, right, in this case. If you go twice as deep, which is this point here, then you do exactly the same thing, and you find out that the amount of water is 20%, and the amount of the DNAPL is 80. And so this, in some respects, kind of jives with this picture here, is that if you go deeper down here, the pressures of the NAPL are larger, and the saturations, because it exists within these little lenses, are also larger saturations of the red stuff versus smaller saturations of the clear stuff, which is water. And so physically, that's exactly what's going on. And so that's the linkage. Capillary pressure behavior we know from the little capillaries, kind of interesting, says something about the mechanisms of what's going on, but that's kind of where it ends. Take a sample, do the experiments on the sample of the capillary pressure versus saturation curves. That gives you saturations at any particular pressure that you apply. But then what you need to do is go into the subsurface and figure out how those capillary pressures vary with depth, which we can do just by rationalizing what we know about water pressures in swimming pools. So this is kind of coming full circle on what we need to know about capillary pressure versus saturation curves. This, because the green curve increases faster than the blue curve, this will always be positive, right? This will always be larger than this, just by looking at this. Green curve is always larger than the blue curve. And so the capillary pressure curve, capillary pressure is always positive here. But we can also look at the case above the water table. And so we can use exactly the same rationale above the water table. So I'm going to zoom in on the other side now and make the same case. This is the ground surface. This is the water table. What do we know about the water table? By definition, the water table is physically the location where the fluid pressure is exactly equal to the atmospheric pressure. So if we use atmospheric pressure, the pressure at the water table is 0. So again, if we're deriving fluid pressure vertically, this is 0, where it crosses this axis. And in the water below this, going down in the swimming pool, this is the same as we did before on the right-hand side. And if we went above the water table, where we're holding the water up by its bootstraps, if you think about it, then it goes at exactly the same slope. Happens to be compressive pressure below the water table. It's in tension above it, because we're physically picking it up in a capillary by interfacial tension. And so this blue line is continuous as we go across here. So that is no different from what we had before. We just didn't draw it as it went across here. What about water? Air. Air behaves in exactly the same way. We know that if we took the pressure at this point here, and we knew what that pressure was, and we went down in the air column, our ears would feel more pressure, and the pressure it would feel would be just, the change in pressure would just equal to the change in elevation multiplied by the unit weight of air. And so the slope of this is going to be controlled by that. We know that the unit weight of air is how much less than the unit weight of water. What's the density of a cubic meter of air versus water? You did know that a year and a half ago. Kilogram cubic meter for air. How much for water? Someone must know. 1,000, right? So this is 1,000 times different. So this green line is basically the axis. It has almost no camber to it at all. And so now we can use exactly the same rationale as before. We can calculate the difference between the wetting fluid, the non-wetting fluid, which is this, and the wetting fluid, which is this. So the capillary pressure is equal to the pressure in the non-wetting fluid minus the pressure in the wetting fluid. The pressure in the non-wetting fluid is air. The pressure in the wetting fluid is water. And so this will be a small number. This will be minus a negative number, so it will be positive. So it will be positive. So this is still positive. And what we can do is the same rationale. We can calculate what the capillary pressure is at this point. It's just the difference between the green and the blue curves. And although this represents an elevation here, it also represents an equivalent capillary pressure 1. And if we know what that capillary pressure is, and we know where we are on the curve, we can calculate what the saturation is. If we go up higher, we can again calculate what that capillary pressure is. This is Z2. This would be P2, or PC2, I guess. We go across here, we find this, and we find the saturation. And so what will that saturation be? This will be, if we want to put some numbers on this is 40% water. And this is 60% air, the Vadose zone. And so that kind of makes sense as well. The higher we go up in here, the less water is present and the more air. And that's just a function of the, again, the same capillary pressure curve that we have. It's exactly the same relationship we had before. Capillary pressure is defined in terms of non-wetting and wetting fluids. This happens to be water. This happens to be air. Nitrogen, basically, I guess, right? And so we were able to say something about the saturations as we go up in the subsurface. So this is a key concept for us. And so it's something that we'll draw on again in the future. And so don't forget it, because you'll need it for sure. So think about this between now and Thursday, and then we can revisit it on Thursday. You think I'm done, right? You know better than that. So give me 2 minutes. So we've covered, it's actually useful to recap everything we've talked about. Everything we've talked about today is really embodied in this one figure, and it's quite important. The ordinates of this figure, as you'll get to know and love, are the ones that we've talked about. Bless you. Physically, this represents what we've called the bubbling pressure, PC0. And it represents the pressure that you have to apply to push a bubble of this non-wetting fluid into the largest pore throat that's in your sample. Physically what it means. As you push that bubble in and you increase the pressure, then you invade more and more of the pore space with that second fluid, and you push more and more of the water out of it. So as you move across to any point here, all you do is you change the saturation of the non-wetting fluid at the expense of the saturation of water. It's physically all you're doing. That's all this diagram means. As you increase this pressure up here, you change the ratios of those two saturations because you're pushing more oil into it and you're pushing more water out of it. You can't push oil into it if you're not pushing water out. As you push more oil into it, it's called a drainage curve because it's draining more and more water out of the system. Once you get to some residual amount, you can't push any more oil into the sample whatsoever, and we call that the irreducible saturation of the non-wetting fluid. SW0, saturation of the wetting fluid 0 means irreducible. Can't get any less than that. If you stop increasing the pressure and you decrease the pressure, then you come down a second curve, and water, which is around this, will spontaneously be sucked in. It'll be imbibed, and you'll move down this imbibition curve with exactly the same behavior as before. As you imbibe water, the saturation of water will increase for any given pressure at the expense of the non-wetting saturation. So that's all these curves mean. If you stop here when you're doing that and now you increase the pressure again, then you travel across these so-called scanning curves. These are called scanning curves. And it means that you go across to this, back to this drainage curve, and then you continue up. So maybe that's not so interesting. It's just important to know that it's there. The other critical behavior is that there's this irreducible non-wetting saturation. Non-wetting saturation, which says something about how much water you can get in, but still leaving this irreducible saturation of the non-wetting fluid. So at this stage, this means that we have, if this is 87%, then this means that this is 13% of oil that's left in the system, and that's interesting to us. It's interesting to us because what it says, don't want to give you whiplash, is that in a physical sense, it says that the geometry of the saturation, if we go back to this figure here, is that once we've pushed as much water into the system as we can, we still have some non-wetting saturation in it. And no matter how much pressure we put across here to try and push this out, it's just going to flow around these blobs, and it's just going to pass water through our system. So it means that if we want to do pump and treat to be able to pull out the non-wetting fluids, it's not going to work. It's going to stay in the pore space, and we have no opportunity to do it. And so really what we've done is through these curves that we've defined, we've said something about how we can remediate systems, and one way in which it actually will not at all work for us. And we can explore that better in due course. Okay. I think that's it.